All right, so here's the setup of the prisoner's dilemma. And the question that a game theory type setup like this tries to answer is like, all right, it goes after the same sort of idea of an equilibrium. If this was the setup sort of in a long-term way, like what is and each individual was sort of acting rationally, trying to, satisfy their own preferences sort of as far as they know them, and responding to the information that they see out in the world. And let's imagine in this setting that everybody has full knowledge of this being essentially the setup, right? So there's no sort of hidden information. Everybody knows that they're playing this climate mitigation game, and they're trying to figure out what the right thing to do is. What's the likely set of actions that are going to be taken? What is the equilibrium that will emerge from this setup? So just to check your understanding real quick, make sure that you can explain, like, pick one quadrant of this grid, and make sure you can explain what actions are happening and what payoffs the players receive. Okay? You should pause the video, make sure that you can explain that, because if you can't put it in your own words, this is going to be a little confusing. Okay? So let's take this quadrant, the bottom right one, where nobody acts, right? We can look and we can see, well, the blue country A doesn't act and they lose $2 trillion. And we can see country B, the orange folks, don't act and they lose $2 trillion. Now, the way to think about an equilibrium is actually due to this guy, we're going to bring another famous person in, John Forbes Nash. The equilibrium that is articulated, it bears his name, a Nash equilibrium. This guy was in A Beautiful Mind, so you might know him more as this guy, Russell Crowe. Anyhow, yeah, that's John Nash. So the Nash equilibrium, the way that you think about it is, in a Nash equilibrium, each player is playing their best response to another player who is also playing their best response. Sounds confusing, but I think we'll first I'm going to define it. Nash equilibrium. Each player plays their best response to each other player who is also playing their best response. Okay, well, what does that mean? The thing that we're going to do is that we're going to look at this situation from player A's perspective and then player B's perspective. Okay, so let's think about player A's perspective, right? And because we're thinking about player A's perspective, we're just gonna forget about player B's payoffs, right? Like, ignore that. So we're gonna look and we're gonna see. We're gonna look first at the. All right, I'm player A. I decide to act, right? And then I can look and I can see, well, if I act and player B acts, I lose $1 trillion. If I act and player B doesn't act, I lose $3 trillion, right? I'm just reading across the first column here, right? Or the first row, rather. Okay, so if I don't act, and player B acts, I lose 0. And if I don't act and player B doesn't act, I lose $2 trillion. So it looks like the best thing for me to do is to not act, right? Because regardless of what player B does, I'm better off. I'm going to lose less if I don't act, right? 0 is less than -1, and -2 is less than -3, right? So my best response is here, right? Now, of course, this is symmetrical, right? So maybe I don't even need to go through it, but like player B is basically looking at things the exact same way. And they're seeing, well, regardless of what player A does, I'm better off not acting, right? Like, I wish that I could control what player A is going to do, because it's going to affect whether I find myself with 0 or -2 trillion, right? But in both cases, I'm better off not acting, right? So the Nash equilibrium here is this inaction situation. And that is kind of a trippy kind of situation, right? It's not the best. We'll get more into why it's not the best, but I think it's worth knowing a little trick to know that you're at the Nash equilibrium. And at the Nash equilibrium, no player would want to unilaterally deviate. At Nash equilibrium, no player would want to unilaterally deviate. Because I can see, some of you are probably thinking, oh, but what about this? What about this quadrant? Wouldn't it be better off if both of them were there? Yes, we're going to talk about that in a second. But the issue is that from this non-action sort of point, neither player would want to act without knowing for sure that the other player would act. Because if they acted, if player B goes from non-action to action, all of a sudden they go from -2 trillion to -3 trillion, right? That's not, so unilateral action doesn't make them better off. And, it's a symmetrical problem. So that's also the case that the other player is considering.